Today's focus is to complete our discussion on Jake's method and also to introduce the notions of antenna diversity and the benefits of antenna diversity. We are going back and forth between simulation, theory, concept, intuition. So, antenna diversity is a concept which you will eventually implement using computer simulation, for which you will use the Jake's method. So, basically Jake's method is our tool that we will use for any form of Rayleigh fading simulation. So, before we get into that, let us just review the concept of Jake's method. Jake's method uses a set of n0 plus 1 oscillators. The relationship between between n0 and n is given. N is a even number but not a multiple of 4. You've got a set of n0 plus 1 oscillators and the frequencies of the different oscillators are given. There's a very deterministic set. But when we go into the implementation, we find that we have some degrees of freedom which is primarily in the form of these multiplication coefficients and also the phases that are selected for the oscillators. So, based on framework was what we had developed in the last class. So, let me pick it up from here. So, here are the oscillators. This represents the oscillators. Okay, this is also an oscillator. And then the scale factors. There is also a scale factor here, cosine alpha. And then we have random phases. These are random phases. And you have them both in the real part and imaginary part. And this is the framework that we have developed. What we had verified in the last class was that ZR of t, if I took the time average, is 0 mean, and so is the imaginary part, which is obtained by these two. So, these are the, and we also had reached the point of, so ZR of t, just it's helpful for you to write it one more time. ZR of t is 1 by scale 2. There are n0 oscillators, scale factor of 2, n is equal to 1 through n0, the multiplication terms cosine beta n or the scale factors cosine 2 pi fn t plus phi n, those are the random phases, plus the multiplicative factor for the last term root 2 cosine alpha cosine 2 pi fd. Okay. Now, if you were to take this portion of this expression, actually it's not 1 by scale 2, it's actually we wrote it as scale 2, right? It's multiplication by scale 2, 1 by scale 2, 1 by scale 1. Okay. So, expected value of, so if I took this portion of it, let me call that as ZR prime of t, this minus the scale factor. The ZR prime of t whole squared time average, that was what we had computed yesterday. I think that comes out to be 2 times n0. And similarly, if we were to compute Zi prime of t whole squared average, it comes out to be 2 times n0 plus 1. So, basically scale 2 has to be chosen such that scale 2 has to be equal to square root of 2 n0, scale 1 has to be chosen to be square root of 2 n0 plus 1. So, that you will get the variances equal to 1/2. So, this will ensure that the following conditions are satisfied. ZR squared of t is equal to Zi squared of t, that is equal to 1/2, and I think that was, please make sure that there is no confusion, that we have changed the figure as well as our expressions. I apologize, I should have written it differently. Okay, the point at which we stopped in the last lecture was to ask the verification of the following expression. the autocorrelation of the complex channel coefficient z of t plus delta t, and you were asked to show a result. I hope you had a chance. This would be expected value. Let me just write it in terms of the time averages. The time average would be the time average of z of t, z star of t plus delta t. You are asked to show that this was equal to a quantity. I believe I have made a mistake in the scale factor. It should have been 2 times summation n is equal to 1 through n naught cosine 2 pi fn delta t plus cosine 2 pi fd delta t. I think I had 4 and 2. I had an overall multiplication factor of 2. That was not correct. This should be the correct value. Can I assume that everybody is comfortable deriving this, or will need to give at least a few hints to get to this point? Everyone's comfortable deriving this result? Okay. Yeah? A few hints. Okay. Again, if it's not needed, I don't want to take time, but if it is needed, I don't mind at all. So basically, what you would have to do is to do the time average of the following: ZR of t plus j times Zi of t, this multiplied by ZR of t plus delta t minus j of Zi of t plus delta t. Okay, this is what you would close bracket time average. Again, like the previous derivations that we showed, anytime you have a multiplication of two different cosines of two different frequencies, the time averages will go to 0, because it will come out as sum of two cosines, and therefore it will go to 0. What you will be left with is terms that are belonging to the same frequency. So if you were to, of course, this product is going to have a real part and imaginary part. Let me just write down a hint for the real part. The real part will contain terms of the following type: 4 times summation n equal to 1 through n naught, basically frequencies of the cosines of the same frequency. So it's cosine squared beta n, cosine 2 pi fn t plus phi n, cosine of the same frequency. So the second term will be cosine 2 pi fn t plus delta t plus phi n. Okay? And then there is the last term, the fd term, that will give you 2 times cosine squared alpha n cosine 2 pi fd times t times cosine times 2 pi fd t plus delta t. Okay, so you see basically cosines of the same frequencies, those are the only terms that remain. You will also find that there are terms of the following from the, you will also find that there will 4 times summation n equal to 1 through n naught. You will get sine squared beta n, basically this term, plus 2 times sine squared alpha n, this term. Okay. So these cosine squared plus sine squares will add up. What you will be left with is terms of this form. Okay, I'll just give you a hint for that. Cosine 2 pi fn t plus phi n times cosine 2 pi fn t plus delta t. This is only the real part, by the way, plus phi n. So product of two cosines, you should get a cosine of the sum and difference frequencies. This can be written as half of cosine 2 pi fn delta t. That will be one term, that's the difference term. The sum term will be cosine 2 pi fn 2t plus delta t plus 2 phi n. Doesn't matter what the phase terms are, basically you will get a cosine of some frequency. If I take the time average, that will vanish to 0. So this this has time average equal to 0 because it's a cosine function. Okay. So what you'll be left with is basically the terms that are of the form cosine 2 pi f delta t. So which if you go back and look at the final expression, that's what is present. So this cosine 2 pi fn delta t, and so the real part has given you this. What happened to the imaginary part? Imaginary part actually completely gets cancelled. Let me just write one step and then we will close that. The imaginary part, again apply the same simplification. What you will find is that you will find terms that of this form, minus 4 times summation n is equal to 1 through n naught cosine beta n sin beta n cosine 2 pi fn delta t minus, so that will be part of the summation. I think I need the brackets. Then it is minus 2 times cosine alpha sin alpha. Basically the scale factors are now cosine and sine instead of cos squared and sine squared. This will be sin alpha cosine 2 pi fd delta t plus you will get exactly the same quantity. So plus the same quantity. So therefore the imaginary part completely cancels and becomes equal to 0. Okay. So it's plus exactly the same quantity. Okay. So you please do verify. Again, it's not difficult, but just need you to be careful with the expressions. So the final result that we have is the following, that the autocorrelation function is of the form that is given in this by this expression. Okay, we are one step away from the answer, so let's complete the discussion that we need for today. Okay, now we are trying to show that the autocorrelation is a Bessel function, right? That's our goal. So here is a result that is very useful for us. J0 of x is what is the Bessel function expression for the Bessel function? If you look up Haken or Molish, any of those, you will find the following: 0 to pi e power j x cos beta d beta. Okay, that's one of the expressions for the Bessel function J0. We will simplify it for our purposes. Again, this is for general, but we are interested in it. So we would like to write it as 1 over pi integral 0 to pi cosine of x cos beta plus j times sine of x cos beta d beta. Okay, that's the rewriting the integrand. And the variable of integration is beta going from 0 to pi, and the only form of the variable that occurs is cos beta. So cos beta is of this type. Okay, from 0 to pi, this is cos beta. Now the actual integrand is sine of that argument. Okay, so since this is a symmetric integrand, the imaginary part contributed by the imaginary part will go to 0, because the sine of this portion will be positive, sine of the other portion will be negative, and when I do the integration, that term goes to 0. So what we are left with is 1 over pi integral 0 to pi cosine of x cos beta, and I think some books already give you the direct expression in this form. And again, applying the symmetries that are present, you don't have to integrate from 0 to pi. Integral 0 to pi by 2 is sufficient, and you can multiply by 2 because you're taking cosine of that. Cosine of minus theta is cos theta. So this will be 2 by pi integral 0 to pi by 2 cosine of x cos beta d beta. Okay, so Bessel function approximated, not approximated, the expression rewritten in this following fashion. Okay, So again, this you can more or less take it as a standard result. Some textbooks may actually give it to you in this form, but the more general form is the one that is given in equation 1. Couple of steps of simplification brings it to equation 2, and this is the form that we are interested in. Now, from your study of calculus, integrals can be approximated by a rule called the trapezoidal rule. Okay, and let me refresh your memory in case you're some of you probably are very familiar with it. Integral a to b f of x dx. This is a very general rule of real integrals. This can be approximated by b minus a by 2n. Supposing I have n points in my so basically if it's a function that I'm trying to integrate between a and b, I'm going to divide it into different values, and I'm going to have n plus 1 points total, okay, including a and b, the n points. So n plus 1 total number of points. In that case, the trapezoidal rule says that the integral can be approximated as b minus a divided by 2n. Think of that as a scale factor into f of I'll just explain in a minute, x naught, x1 all the way to f of xn. There are a total of n plus 1 points where xk is equal to a plus b minus a divided by n into k. So it's a linear interpolation of the range between a and b, and you are sampling your function at each of those values. The trapezoidal rule often that you would probably be familiar with is the first and last terms have got slightly different weighting than the middle terms. The middle terms all have a scale factor of 2, so basically it will be all the way up to 2 times f of xn minus 1, and then f of x naught and f of xn have got a scale factor of 1. But basically it is this 2 basically offsets the scale factor of 2 that is happening there. So the b minus a by n is the area of your those trapezoids. Okay, so basically the trapezoidal rule says you have to add the areas of those trapezoids. You may give slightly different weightages for the first and last trapezoids. Again, depends on how you interpret the trapezoidal rule and how many sampling points that you get. Okay, so but basically this is a form of the trapezoidal rule. So the observation is the following, that you have to evaluate the function evaluated at n plus 1 points. Evaluated at n plus 1 points, and you get to decide. If you want to have a tighter approximation, you would take larger number of values. Okay, n plus 1 points, they are denoted as x naught, x1 and xn. x naught is equal to a, the starting point of the integral, xn is the ending point of the integral, and basically it's linearly interpolated in that range. Okay. And we also note that you have a 2x weighting factor for the following points, which is x1 all the way to f of xn minus 1. Okay, so except the first and last, you get slightly higher weightage for a factor of 2, but the important point is that you preserve the area of the trapezoids and do the integration. Okay. So now comes the important part, and then you appreciate the insight and the practical engineering mind of Jakes. Says, okay, I have to eventually approximate J0, which is 2 pi fd times delta t, and this we have shown to be equal to 2 by pi integral 0 to pi by 2 cosine x cos beta d beta. Okay. Now, if I were to tell you, please apply the trapezoidal rule to this Bessel, this integral that approximates the Bessel function. Okay. So then we will leave this 2 by pi alone, that's a scale factor, does not affect us. Upper limit is pi by 2, lower limit is 0. I'm going to divide into n naught plus 1 points. I think you will start to see where the similarities are coming. N naught plus 1 points is what I'm going to do in my approximation. So then it becomes pi by 2 minus 0 divided by 2 n naught. This is the same as pi by 4 n naught. Okay, that's another scale factor. The first one that, and if I call this as x, let me call this as x. So the first term in the trapezoidal rule will be cosine x, because beta will be 0, cos beta is 1, cosine x. The second term in the trapezoidal rule will be basically beta uniformly separated between 0 to pi by 2, and you're going to increment it. So the next term is going to be a scale factor of 2 cosine x times cosine pi by 2 n naught into 1. Am I right? That's your pi by 2 n naught is your the spread, and into 1 because this is the first component of that. Okay. Second one will be pi by 2 n naught into 2, pi by 2 n naught into 3, so on and so forth, and the last one will be pi by 2 n naught into n naught. Okay. So please fill in the terms. The last but one term will be 2 times cosine x times cosine pi by 2 n naught into n naught minus 1, plus the last term will be cosine pi by 2 n naught into n naught. Okay. That's trapezoidal rule applied to the integral that approximates the Bessel function. If you just take a minute to just make sure that you are comfortable with that, because what the trapezoidal rule says is the variable of integration gets uniformly divided in the range of the integral, and then you apply it to the function, and that's exactly what we have done and obtained this expression. Okay. Now we are just one step from the answer. Can you please see what this expression is? Is 2 pi fd times delta t into cosine pi by 2 n naught. Is that correct? So if you rewrite this as this is equal to 2 pi fd cosine pi by 2 n naught into delta t, starts to look like the oscillator that Jakes was using. And if you go back and verify, it is very, very close. It's not exactly. So what was the expression that was used for F1, the first oscillator? Basically in the expression, what you would have got in the Jakes model, this is what you would have obtained. Jakes model, the first one would have been cosine 2 pi f1 delta t. Let's say if you wanted to approximate that, this would have been equal to cosine 2 pi fd. If you go back and look at the expression, it will be cosine 2 pi by n. Go back and look at the frequencies, into n is equal to 1 and then delta t. This can be rewritten where n is equal to 4 n naught plus 2. We use that relationship and rewrite this in the following way. We write this as cosine 2 pi fd into pi divided by 2 n naught plus 1 times delta t. Okay. And basically the oscillator frequency is slightly different. Basically you will have to compare this term and this term, and of course cosine of that, and you find that the terms are matching. Now, the term cos x is actually matches precisely because that corresponds to cosine of 2 pi f d times delta t. So this matches perfectly. All those oscillators are very closely approximated. It's in the trapezoidal approximation you will get 2 times n naught. In the what Jakes has used, you get 2 times n naught plus 1. Again, why did he choose that n naught plus 1? Probably some other reasons we don't know. This is how he had chosen it, and we find that it's a pretty good approximation anyway by the trapezoidal rule. So we go back and revisit the result that that Jake's expression gave us. Summation or a time average of z of t, z star of t plus delta t, which comes out to be 2 times, which we have verified to be equal to n naught equal to n naught cosine 2 pi f d fn times delta t plus cosine 2 pi f d delta t, where fn is given by 2 pi divided by n into n. Okay. So basically, let me make sure that's the correct expression that we have. Is that correct? Are the expressions for the oscillators correct? Yes, 2 pi by n into n. Okay. 2 pi by n into n. So and this we can say is a approximation, a fairly good approximation, and the approximation gets better as n naught or n becomes large, and this is approximately some constant into j naught times 2 pi f d times, this is, wait, I have written something wrong here. This is f d times cosine 2 pi by n into n, right? Yeah, please catch me if I am making such mistakes. 2 pi f d times delta t. Okay. So the Jake's model does the following for us. Establishes that you get ZR of t, the time averages are a zero mean. Let me just write it like this. ZR of t, Zi of t are zero mean. They also have the variance is equal to 1/2. So Zr squared of t time average is equal to the time average of Zi squared of t equal to 1/2. So if I write down expected value of mod z squared, this comes out to be equal to 1. Okay, and so it's got the correct variance that we want. It also has the correct expected value of z of t, z star of t plus delta t is a stationary process which gives out some constant times j naught 2 pi f d times delta t. So it satisfies the important things of zero mean, the proper variance, and the appropriate time correlation that we need. So how do we use the Jake's model? Jake's model asks for 3 inputs. The first one it asks you is how many oscillators you have to specify. Okay, and the thumb rule is n naught greater than or equal to 15. You can take 20, 25. The higher the number, the approximation becomes better. Now, what is the drawback of choosing a large number? Remember, these oscillators have to keep running. So in order to get the next sampling and the next value of Zr of t or Zi of t, you must get those cosine components. So basically, you'll have to keep incrementing those oscillators. But it's just a simple operation when you are doing it on a computer. Okay, you have to first specify n naught. Second, you will have to specify what is your maximum Doppler frequency, and then you will have to specify the duration of the waveform. that you need, duration of the waveform. Okay? And basically this is what we need to in the, so you specify inputs to Jake's model. Inputs would be the maximum Doppler, the number of oscillators N naught, and the length of the fading waveform. Let's call that as N length of the fading waveform. Now we also have to make another choice, the random phases of these oscillators, phi 1 to phi N naught. These are chosen to be random, uniformly distributed random variables, chosen randomly in the range minus pi to pi. So basically some random phases are sufficient. Then we start running the Jake's model and generating the samples. The samples are taken as Z of n to be equal to ZR of n plus j times Zi of n. These are the samples at the specific values. What we have done, we have taken t and set it equal to n times ts, where ts is equal to the sampling period that you are trying to simulate. And as an example, in the case that we have considered, if I had a 24.3 kilosymbols per second system and I was doing 8x oversampling, then my sampling frequency is 194400 hertz, and T sampling will be equal to 1 over Fs. Okay, that's what you would increment, because ultimately these oscillators are going to ask you, tell me what is the value of T. You're going to start at some point and keep incrementing. Each time you increment by the sampling period. Okay, and depends on what oversampling factor you want. And notice that everything else is in this picture is frozen. Alpha is fixed, all the betas are fixed, the phases you have chosen, each time you just supply the value of T, it will give you all the cosine values, you multiply and add with the appropriate scaling, and then that becomes your fading coefficient. Okay. And it turns out that this is a very effective way of generating Rayleigh fading on a computer, which satisfies the statistics almost exactly as you would see in the real world in terms of the fading statistics that we would observe. Any questions? Definitely, please take the time to work through the numerical parts so that you can feel comfortable with the results that are presented. Okay. Now, there is a paper by researchers Dent et al., which I would ask you to read. I will upload it onto the on the website, and the gist of what they are proposing is the following. This is Jake's model. The oscillators were chosen to be one at Fd and then equally spaced with the spacing of 2 pi by n, right? The spacing was 2 pi by n, and the last one was before pi by 2. So the last one was at pi by 2 minus pi over n. Now, this is Jake's. Dent et al. Did a slightly different approximation, which they said what they said was so the frequencies that were chosen were starting from the Fd itself. What they said was anyway you're trying to do an approximation to the integral. So it does not make a difference if your the first oscillator is not at Fd but slightly offset, and the last one is also offset. So basically it's a different sampling grid of the oscillators. But notice that neither FD nor pi by 2 are present, you are basically in between, same number of oscillators. Same number of oscillators that are again the spacing is the same, slightly different grid that is used. Okay. Now the difference is that the approximation that they have proposed to the Bessel function is that you can now write z of t to be equal to n is equal to 1 through n naught cosine beta n plus j sine beta n into cosine 2 pi f n t plus phi n. Okay. So if you want to put a factor of 2, it does not matter. So basically all the oscillators have got same scale factor, same weighting. There is no, the one particular one does not get any special treatment. And they have shown that this is also a good trapezoidal approximation with the n naught being sufficiently large. Okay. So the key point of the method is, one is the claim is that this is this works better than the original Jake's model. We are not as much interested, maybe that's a useful result for us, but a more important result for those of you who are already have worked in wireless communication, you will appreciate this. Let me call this as a n of t, the part which is in the green bracket. Okay, so this is nothing but, I'm going to for the moment I'm just going to ignore the 2. Summation n equal to 1 through n naught a n of t. Okay, this is how you would write z of t. Now why is this important and what are the benefits? Basically this paper by Dent et al., why do we even want to read it? If it's just another approximation, why not just accept it? Okay, we'll just take this. But there is a very important offshoot of this result. The result is as follows. This can be written as 1, 1, 1 in vector form times a naught a1 of t, a1 of t all the way to a n of t. Now you may still be wondering there's nothing new that we have gained in this whole process. Just wait for a result that needs to be embedded here. There is a series of matrices that we encounter in the context of CDMA, but it's very useful in this context as well, called the Walsh-Hadamard matrices. Walsh-Hadamard matrices. It's a family of matrices which is derived from a basic matrix. At the lowest level, the matrix is just a 1 by 1. Then it becomes a 2 by 2. It becomes 1, 1, 1, minus 1. So the matrix is repeated 3 times without a sign reversal. The 4th time it is repeated with the sign reversal. The next level of the family, it becomes 1, 1, 1, minus 1. That's the first repeat. 1, 1, 1, minus 1, 1, 1, 1, minus 1. Third repeat, and the 4th one has to come with a sign reversal, minus 1, minus 1, minus 1, plus 1. Okay. Now you've seen the pattern. You can increase. You can work on it. The general formula is the next higher level in the Walsh-Hadamard matrices is given by, take the lower level matrix, repeat it 3 times, and the 4th time you take it with a minus sign. Okay, it's very important that you don't miss this, and that is the Walsh-Hadamard matrices. The beauty of the Walsh-Hadamard matrices is that H Hermitian H is equal to I. Any of these Walsh-Hadamard matrices, if you take its transpose and multiply, because real matrices, Hermitian is the same as transpose conjugate is the same as transpose. So H Hermitian H you will find that these, so basically these rows and columns are orthogonal to each other. It's a very, very useful property that is present here. Okay. Now, if I now write the following result, Z1 of t all the way to Zn naught of t to be equal to a Walsh-Hadamard matrix of the appropriate size times A naught of t all the way to A n naught of t. Okay. So, what I have done from the previous line, I took the same functions A naught to A1 and rewrote it and wrote in terms of the Walsh-Hadamard matrices. So, this first element is the same as Z of t that I was trying to generate, correct? That is basically the first row is all ones. So, the first row is all ones, but the beauty of it is you now have other functions which are basically derived from the original set A naught to A, sorry, it should start with A1 to A naught. But the beauty of it is expected value, if I call this as some Z matrix, Z Hermitian Z will mean A Hermitian, let us call this as A matrix, this will be A Hermitian, A Hermitian, H Hermitian, H times A. H Hermitian A is a diagonal matrix. So, then what do you find? You find that all these Z1 through Zn naught are what type of variables? There is no correlation between them. They are all uncorrelated variables because the correlation matrix is a diagonal matrix. That means they have only correlation with themselves. They are not correlated with anybody else, any of the other functions. So, this Z0 through Z1. So, this basically means that Z1 of t, Zn0 of t are all uncorrelated with each other. Okay. Now, the beauty of it is this is exactly what we will want to assume when it comes to diversity. Okay. And that is why this modified model is a useful model which is proposed by Dent et al. And since you are all PG students, I would like you to get the feel for, this is how research progresses. Somebody proposes something, he has some basic structure, somebody else thinks up, what, I cannot extend it using Walsh-Hadamard matrices because there is this one has got a different scale factor. Can I do a different approximation? Yes. Then I can represent it in terms of this form. Then link it to the Walsh-Hadamard matrix and then get uncorrelated sequences. Now, didn't Jakes know that you had to get uncorrelated waveforms for fading? Answer was he knew. Okay. And his way was, how do I get uncorrelated fading out of this one? So, he said, well, the only thing that I can ensure that is, see, all the betas and alphas have been frozen, right? So, what you really didn't fix was the phis. So, what he said was, okay, you generate one set of random phases, let us call them as phi 1 1 all the way to phi n naught comma 1, and then he said, okay, generate another set of random phases, that will be phi 1 comma 2, phi n naught comma 2, and let us hope that the waveforms are uncorrelated. But he really had no way of telling you, okay, I can guarantee you that things are uncorrelated, because they actually tried this and found that in some cases it worked very well, uncorrelated waveform. In some cases it is not working very well. There is a residual correlation, whereas the method proposed by Dent et al. Says very clean, there is no issue of residual correlation. This will assure you that the correlation is exactly as you want it to be. Okay? So again, part of the course is to expose you to some of the milestones that happened in terms of research, and this is a very useful one that is present. I'd like to just take a few minutes to introduce you to diversity before we end today's lecture. And our starting point for diversity will be an intuitive experiment, and time permitting, I would like you to try it out on the computer as well. So this is the experiment that you have already done. AWGN, you have a nominal SNR, this is and you generate instantaneous SNR as alpha squared EB by N naught. So basically there will be some perturbation of the SNR around the nominal value, and you calculate the BERs, you took the average, and then you obtain the result that is. So the steps that you followed was you generated different alpha n's, right, instantaneously you generated that. From that you will calculate gamma n, which is alpha n squared EB by N naught. Then you calculated the BER of that particular trial as Q of square root of 2 times gamma n, and then you finally average the BER and said that this is the BER expression. Let me call 1 over n, n is equal to 1 through n, BER n. Right? Am I right? This is what you have done in your computer experiment, and you were able to show that the graph is something of this type. Now I want you to try this following experiment. For each of those trials, instead of generating one random variable, I want you to generate 2 random variables, alpha n comma 1, alpha n comma 2, independent, and the SNR is going to be the maximum of the following: alpha n comma 1 squared EB by N naught, comma alpha n comma 2 squared EB by N naught. Each of these random variables is going to give you an instantaneous SNR. I give you the benefit saying you get to pick the better of the 2, and BER n is the same as before, Q of square root of 2 gamma n, and BER average also that you have obtained, okay, like before. Will the graph be any different? Will the graph be different? So is the problem clear? I generate instantaneous values of Rayleigh fading, and then I square it to get the instantaneous SNR. It may turn out that my instantaneous SNR at this point was here. Okay, that was when I did only one trial. But when the second experiment that I want you to try, you're going to generate each time 2 Rayleigh random variables, and I'm going to pick the better of the 2. Is this graph going to change? BER graph going to change? Yes, and it will change for the better. So what you would expect is that it's going to be somewhere lower, right? It can at worst it can be the same as the red, but it will hopefully be lower because you get to choose the better of the 2. You may end up with a lower BER, and therefore your overall average is also going to go down. That's the starting point of our intuition regarding diversity. If you have a choice of more than one copy of the signal, and if they are uncorrelated, it's very likely that one of them has got a better SNR. You should be able to get a better BER than if you had only one copy of the signal. So that is, with that as the starting point, we're going to build our intuition on the whole. Diversity is a very vast field, but what we would like to do is what is the essence of the concept of diversity, how do we exploit diversity, and how is it exploited, or how is it used to our advantage in the 4th generation and going forward into the systems. Okay, so that is our starting point. We will pick it up from here in tomorrow's class. Thank you.